Good afternoon, everyone. Welcome to this live. processes like dissociation, which is a very important one at high temperature. So the combustion gases can actually dissociate to get back to carbon and oxygen or nitrogen. And also there are different kind of reaction chemistry that may get activated at higher temperatures. So fuel air cycle, which is a significant improvement over the air standard cycle, allows us to get a more realistic estimate about the real engine operations. And on top of the fuel air cycle, if we add some more real life factors like the so-called time loss, like the heat rejection to the surrounding, like the exhaust blowdown loss, etc., what we get, that is the actual cycle. We have there also talked about the valve timing diagram. That is in ideal cases, like in ideal air standard cycle, the opening and closing of the valves are instantaneous. But in practical cases, the valves definitely need certain amount of time to open and also certain amount of time to close. And that's where the role of the valve timing diagram comes into picture. By properly timing the opening and closing of the valves, we can ensure greater amount of fuel intake into the system and also the most optimum power output and therefore the optimum thermal efficiency. But we have to very minutely control the opening and closing angles or closing positions of the valve. So that's what is the in the valve timing diagram. And after that, we have also talked about in module 6 the gas turbine cycles. Now, gas turbine cycles can also be viewed as what I can say are cycles working on combustion gases. However, these are open cycles, whereas air standard cycles are reciprocating cycles and generally work in closed mode. Like combustion gas is trapped inside the cylinder where it gets compressed or it gets expanded, and then after the entire operation is done, it is released. However, in case of gas turbine cycle, which is a rotary cycle, the combustion it operates continuously. The combustion, as it happens, the combustion happens outside the actual turbine. What I can say, that's why this is a kind of external combustion cycle similar to the steam power cycle or steam turbines. And the combustion gases which are produced in an outside chamber enters the turbine where it produce the work output. So gas turbine has the capability of producing very high amount of power. Also, it reasonably high efficiency. So you have talked about the gas turbine cycles in chapter number 6. The most ideal cycle for gas turbines is the Joule cycle or the Brayton cycle. We have talked about the basic Brayton cycle. Then we have explored different ways of improving the performance or efficiency of a Brayton cycle, like the intercooling between two stages of compression, which is used to lower the temperature of the gas, accordingly reduce its volume, and therefore save the work required for compression. We have talked about the reheating between two or multiple stages of the turbine, so that we can get higher work output from the turbines. We have talked about the regeneration, and accordingly we have seen different ways of improving the gas turbine cycles. Of course, lots of different designs, improvements, etc. that have been discussed. In chapter number 7, we have talked about the vapor power cycles, which is in complete contrast with the combustion gases based cycles like air standard cycles or gas turbine cycles. Now, steam turbines are external combustion engines where again the combustion happens in a furnace. We can say somewhere closer to the boiler. And here the combustion gases actually are not the working medium, rather the heat or thermal energy that is available in the combustion gases that is transferred to secondary working medium, which is water. And after absorbing that energy, liquid water gets converted to vapor phase, and that vapor is used as the working medium in the turbine, in the steam turbine. So we have talked about the basic Rankine cycle, which is the idealization for any case of any vapor power cycles. Then we have, similar to gas turbines, we have talked about different improvements on that, like reheating and regeneration, both are possible. It is in practical cases, a steam turbine plant may have multiple stages of the turbine. We have HP or high pressure stage, we have LP or low pressure stage. We sometimes may have an intermediate pressure stage as well. And the reheating between two such stages increases the power output. Of course, we have to keep in mind that reheating also increases the total amount of energy added. So reheating may or may not cause an increase in the efficiency. However, reheating definitely provides you higher power output from the cycle. Whereas regeneration doesn't regeneration actually reduces the work output slightly, but it has the what I can say the potential of significantly increasing the total or the net thermal efficiency of the plant, because it substantially can reduce the heat required by the fuel or by the working fluid. So we have talked about the vapor power cycles in the module number 7. And then in the module number 8, we have talked about the cogeneration or combined cycles, which actually is an amalgamation between the gas power cycles and the vapor power cycles. Often their working fluids are different and their working temperature ranges are also different. And to take care of that advantage, we can go for a combined cycle. Like we can have something like a gas turbine cycle as a topping cycle, and the heat that is rejected in the cooler of a gas turbine, that can be supplied to a liquid like water, and that water can now operate in the Rankine cycle. Accordingly, we can have a Brayton cycle as a topping cycle and a Rankine cycle as a bottoming cycle. And as the Rankine cycle doesn't need any separate source of energy, rather it is working more on the heat rejected by the topping cycle. So we are not spending any additional amount of fuel energy, but we are getting power output from two different sources, the gas turbine as well as the steam turbine in the Rankine cycle. And so we are having greater power output and substantially greater thermal efficiency. So the combined cycles or cogeneration process has the combined cycle, I should say, provides us a way of getting substantially higher thermal efficiency, so significant savings in the fuel requirement. And cogeneration is actually associated with the same thing. Here, not only power, we can talk about cogeneration means simultaneous generation of something else also. Like we may be talking about simultaneous generation of power and purified water. So these are cogeneration plants. So up to this module number 8, we have talked about the power producing cycles. From module number 9, we are talking about the power absorbing cycles, and we are exploring the refrigeration cycle in the module number 9. Now, the ideal vapor compression refrigeration cycle is the point with which we are starting the discussion of refrigeration cycles. An ideal vapor compression cycle can somewhat be viewed as a reverse Rankine cycle. Means if we reverse the direction of all the arrows in a Rankine cycle diagram, what we are getting is a vapor compression cycle. However, there are differences in the range of their operations, and accordingly, we need to understand the operating principles of a vapor compression cycle separately, and also the ways of improving its performance. We have to keep in mind here we can't define any thermal efficiency, because here power is not output, rather input to the system, and thermal energy is the output from the system. And accordingly, we can define a coefficient of performance, again, depending upon what is our actual objective, whether we are working on a refrigerator or a heat pump, our definition of coefficient of performance can be different, but the operating principle remains the same. So we are talking about the ideal vapor compression cycles. We have talked about the refrigerant, the naming convention of refrigerants, how we need to, the synthetic refrigerants, so-called the freons, and how we need to phase out the freons because of the environmental concerns, because of their ozone depletion potentials, global warming potentials, etc. We have we are also talking about the other major alternative to the vapor compression cycle, which is the vapor absorption cycle, which generally has much lower COP, but it generally works on some waste source of energy or some low temperature source of energy, and it can be extremely efficient, particularly for large scale applications like some centralized air conditioning applications. The vapor absorption cycle generally is highly adaptable, highly efficient. In the 10th week, we shall be talking about the gas mixtures of ideal gases or mixtures of real gases, something like air. What is air? Air is nothing but a mixture of multiple gases. Now, if we consider each of these constituent gases are ideal gas, then the mixture that we shall be having is an ideal gas mixture. if even a single one of those constituents are not ideal or is not ideal gas, rather it's a real gas, then we are dealing with a real gas mixture. So we shall be talking about how to estimate different characteristics, different properties of a gas mixture in this module number 10. And in module 11, we shall be talking about the properties of gas and water vapor mixture. And that actually is the field of air conditioning, because whenever you're dealing with an air condition, we are talking about using atmospheric air, and atmospheric air can have significant amount of moisture content. So the controlling the temperature as well as the moisture content of the conditioned air is the objective of any kind of air conditioning system, and that we shall be seeing in the module number 11. And then in module 12, we shall be wrapping up, but I shall be talking about that later on in the third live session that we may be having in this course. But in this live session, I can see there are no participant, or at least I have not received any kind of query from your side. So if queries are not there, then maybe we can stop this live session. But of course, if you have any questions anytime, you can write to the course portal. I shall be tracking that. Our TAs, our PhD scholars are also there who are regularly monitoring the monitoring the course portal, and we shall be happy to respond to any of the queries you have. But for the moment, I will wrap up this live session. Please study the lectures, see the lectures properly, and also please go through the books also, because no class lecture, no lecture notes are sufficient. Rather, books have definitely no alternative at all. That is still the best possible way of learning any subject. So go through appropriate books. Books have already been suggested as a part of this course page, and you can collect any of those books and go through that. But for the moment, I'd like to wish all of you well, and like to say bye to all of you in this live session.